fine?
Yeah, perfect. Thank you. Can
Great.
start.
Yes. Okay, so good afternoon. My name is Jerzy Szałapak, and I'm very happy to be here with you. I will start with saying a few words about our scientific team. Then I will speak of some of the problems concerning electronics development, with the focus on flexible electronics. And after that, solutions within use of low temperature joining technique and adhesives will be shown. So, as already it was mentioned, I'm from Warsaw University of Technology, and I'm a member of Professor Jakubowska's team. Most of our research is conducted in the university lab facility called Center for Advanced Materials and Technologies, where our team has created a printed electronics, e-textiles, and assembly department. My main responsibility within the team is the assembly part. Among our projects, we have T-shirts with a flexible display that can be bent, folded, and washed. Smart Heal, which is a non-invasive and cheap diagnostic tool for chronic wounds, enabling immediate detection of changes in pH correlated with inflammation, and thus the selection of an appropriate treatment without removing it, which allowed our PhD students to win 2022 Dyson Award. We have also methods for joining on various flexible substrates that would survive bending, folding, stretching, and washing in washing machine, or open heart electrodes that for EKG that were already tested during an operation on a pig. I should mention the pig later on ran through her garden. So, electronics as we know it sticks to rigid circuit boards and complex packages. We stick to it due to its existing production lines and thermal conductivity requirements. But these technologies are not enough for many uses anymore. So we have an alternative. We have printed or organic electronics, which stands for a revolutionary new type of electronics, also called emerging electronics, which is thin, lightweight, flexible, robust, and produced at low cost. Emerging electronics means electronics beyond the classic silicon approach, including flexible printed electronics from organic, polymeric, or inorganic materials. The organic and printed electronics technology also enables a wide range of electrical components to be produced and can be directly integrated into low-cost, reel-to-reel processes. So such electronics may be made with techniques well known from newspaper and packaging printing. It can be screen printing, flexography, roll-to-roll, and many more. As consumers' habits change and they switch to reading on phones, computers, or e-book readers, printing companies are looking for a way to stay on the market. The production of printed electronics is such an opportunity. Every day, there are press reports about new uses of electronic devices. You can read, among others, about innovative devices for testing biological parameters of the body, flexible displays, electronic tattoos, or devices for more efficient charging of batteries in electronic cars. In the pictures, you can see some of the ideas of such products. In this case, made by us or by our friends from IZM Fraunhofer, with scientists from where I developed some of the materials that may be an answer to the problems discussed during the presentation. So, current rigged electronics are moving towards higher powers, and hence higher operating temperatures and better thermal conductivity of the connectors are needed. Also, we want to manage the battery life better. That still requires improvement of heat transfer to improve the efficiency of the products, because more than 30% of the power is used for cooling. On the other hand, we still have this new wave of innovative devices which require flexibility or even stretchability of conductive paths and joints. All of the problems above are still valid for flexible electronics. I would already say that wire mounting or bonding is not a competition for mounting to substrates, because It is for top connections without the requirements for heat dissipation and some management with the wires issues. It should be treated as a complement to joining, that is sintering, adhesives, or soldered joints, and not as an alternative. Additionally, we should mention the restriction of hazardous substances directive, so-called RoHS, already well-known directive that eliminates lead from electronics and causes some problems with the replacement, and general aim for waste reduction, requiring biodegradation or at least recycling of used materials. So, concerning joining in electronics, soldiers are not flexible. In most cases, the melting temperature of the joint materials are below 250 degrees. In general, soldiers don't have operating temperatures for high power electronics. Alternative is brazing, but minimum temperatures are above 450 degrees. So there's a void between 200 and 450. For flexible electronics, and it was mentioned by the colleagues before, adhesives, we have issues with the temperature as well, but in here we need much lower temperatures. For flexible electronics, the most common idea are adhesives. Some of the carriers may be flexible, but achieving that with maintaining proper conductivity and proper mechanical parameters is a challenge. And I will tell you a bit more about those challenges later. In the context of today's climate and environmental challenges, electronics, even flexible electronics, need to be designed more consciously. We're talking about materials, processes, and end-of-life thinking. It's not just technology, it's responsibility. And we are already using biodegradable paste and substrates in our work, but the biggest challenge remains reconciling this with technical requirements, conductivity, durability, and scalability. On the other hand, we cannot forget about the performance. No company and no user will switch to different solutions unless they see their own gain, or at least no loss in such a change. No new material and no techniques can be worse nor more expensive than the ones we already are using. It is the scientist's role to balance the performance, both electrical, mechanical, and the ecological footprint. It's our role to find better applications, better materials. And it's the ongoing research that helps us to reduce the cost and scale ecological alternatives. Okay, so let's hop to the assembly. We'll start with joints for flexible electronics. In general, adhesives are considered as the main idea for flexible electronics. And adhesives can have various properties. We can adjust mechanical strength, resistance to various environments and chemicals. We can even try to adjust the impact on the environment. Although it is crucial to remember that the shear strength of the adhesives is limited. And it is even more limited when we consider adding conductive particles into the carrier. Let's be honest. The more particles we add, the weaker the adhesion will be. It's quite logical because we are reducing the amount of polymer, which is the sticky part of the conductive adhesive, responsible for the adhesion and for the cohesion. So on one hand, we want to achieve as high electrical and thermal conductivity as possible, but on the other, we still need the mechanical and other parameters. And it would be great to have at the same time flexibility, washability, biodegradability, or at least compostability, etc. And this is the moment we realize that what we aim for is good enough. We don't have any holy grail. We need to choose. We have to distinguish the adhesives for different purposes. I'll show it to you on an example in a moment, but first I want to show you the main possibilities of adhesives that are on the market. So first option, and let's be honest, most commonly used, we have one component, heat-cured conductive adhesives. Most commonly with silver particles containing 70 to 85% of metal particles by weight. That, of course, impacts the printability, although most of these adhesives are adjustable for automatic dispensing, eventually for stencil printing. Screen printing requires a bit more viscous paste. Anyways, in rigid electronics, curing in 120 or even more degrees is very common. The issue is with bending, even more with stretching. But most of the materials proposed for flexible uses, especially the ones actually working, are one-component heat-cured adhesives. Concerning electrical properties, these are the adhesives with the lowest resistivity. But the curing temperature still can be an issue. Also, shear stress resistance may be not enough. Due to the temperature requirements and search for higher mechanical strengths, two-component adhesives are widely considered. We can find quite many options on the market, from MG Chemicals through Panacol, etc. Although not all of them are room temperature cured. The ones that actually are tend to have quite high shear strength resistance. But on the other side, the resistivity of these adhesives is higher than for one-component materials. And what's more, most of them are quite brittle. They do not perform well in bending tests. At least the ones I had the chance to test were breaking within first few testing cycles happened. The ones that were additionally cured with temperature performed much better both electrically and mechanically. There are more and more materials like that on the market because of the need for low or even room temperature curing. But I personally haven't found yet even one that would be worth using, at least in comparison to the ones discussed before. I presume that is why quite a strong attention is put towards UV curable adhesives. Well, that and curing the adhesives within seconds. That, in comparison to other adhesives, would greatly improve the speed of production of the sample, especially with all the roll-to-roll or rotary screen printing, etc. methods that are crucial for printed electronics. But there are limitations here, and they are quite big. Electrically, it's not bad. Comparable to two-component adhesives, maybe even better, although not as good as the one-component ones. But there is quite an issue with the mechanical parameters. Well, whether you think of conductive pastes, 3D printing, or other techniques based on UV curable materials, they usually require additional curing. And even then, the mechanical properties are clearly inferior to the previous options. Similarly to two-component ones, I haven't found one that would be reliable enough for the uses our team has. All in all, I personally prefer to stick to the heat-cured ones, at least up to date. Although I really hope for the UV-cured ones and that they will improve. Although it's hard to think of UV-cured polymers as a very sustainable ones. Currently, typical UV-cured conductive polymers are neither biodegradable nor easily recyclable, but research on their green versions is ongoing, and there are already some promising directions. Again, one can debate when we talk about sustainability. The energy required for UV-cured materials is quite low, so it already is an advantage. Also, work on UV-curable resins based on starch, on cellulose, PLA, or lignin is ongoing. In addition, biological derivatives are also being worked on, which reduces the carbon footprint on production. Heat-cured materials have highest problem with energy required to cure the joints. So the lower the temperature of the process, the better. And on the market, we can find quite a lot of materials that require no more than 60 degrees for curing, although the curing time may be not 5, but 15, 20, or even 30 minutes. Other parameters depend on many factors, but they are still better. The outcome, the sustainability, apart from the energy part, is still better than for two-component chemically cured ones, especially since they require hours to be cured in many cases to achieve proper parameters. And now the promised example. A few years ago, we needed a material for an adhesive for thermal shrinking foils. The issue was that instead of 70 degrees, that thermal resistance of these foils was 50 degrees. 15.1 was already too much, and the substrates would break, would shrink, would deteriorate. So we covered over 50 different variations of adhesives, polymers, particles, residues. We tried UV cured ones, chemical cured ones, etc. And there was always some issue, whether it was conductivity, brittleness, or just mechanical bendability. So with Dr. Vitaly Szczenev from IZM Fraunhofer, we developed a formula for so-called VJ pastes that may be used for both paths and joints. The formula was tested on various substrates in various conditions. In 60 degrees, we were able to achieve sheet resistance of 18 milliohms per square. That means that the resistivity of the layer is lower than of the best adhesives on the market, well, at that point. Shear strength wasn't very impressive, but it was comparable to other materials like that. And it is flexible and stretchable. To improve mechanical properties and additionally create a barrier against moisture and oxygen, lamination or encapsulation may be used. Lamination requires higher temperatures and additional pressure, which is too much for some materials, especially stretchable ones. We used encapsulation, which is basically a polymer glob top, so polymer droplet placed on the top of a chip. It allowed us to double the mechanical parameters. Encapsulation polymer needs to be stretchable as well if we are aiming for stretchable substrates, so only certain types of materials may be considered. And so our joints were tested mechanically for bending and stretching for 10 and 20%. And the resistance rise of the samples never exceeded 20%. The joints were also folded multiple times and washed in the washing machine. Washing machine tests conducted by Sigrid Rotzler from IZM confirmed that we are able to make joints surviving 10 half-hour delicate washing cycles, and it's all still in 60 or less degrees. And going back, so there's a lot going on within the adhesives. Concerning the electrical and mechanical parameters, it is worth mentioning one of the most interesting approaches that occurred on the market about a year, maybe a year and a half ago. It's the Z-Tac adhesive by Sunray Scientific. The main idea here is that they use special magnetic board of their design during the curing process, which aligns metal particles in the joint. The conductivity is comparable with the best adhesives in the market. Mechanical properties are higher, mainly due to the high percentage of polymer within the adhesive. And we don't have any risks concerning short circuits. You can apply the adhesives on the whole chip. The current will work only in Z-axis anyways. The adhesive is also claimed as a very flexible one, allowing for work in e-textiles or even after some adjustments with liquid wires. The main issue here, and I'm once again mentioning the holy grail, is that it's not that sustainable. Although the curing temperature can be easily reduced below 100 degrees. Finally, more sustainable materials are rising. Such materials are very actively researched right now. They are usually based on biodegradable or compostable matrices. The fillers are, as usually, carbon or silver-based. Main issues are conductivity, degradation, or mechanical. Use is dependent on the type of the techniques that are of the samples. Of course, for the single-use equipment, the requirements are lower, although it still needs to be reliable. As polymers, the most common materials are PLA, silk fibrine, gelatin, cellulose derivatives. And at that point, I want to mention that we are also working on adhesives and paste based on such polymers. Well, as we heard before, a lot of teams do. We still have some adjustments to do, but currently we achieved electrical parameters comparable with typical adhesives available on the market. The carrier is made in such a manner that it's actually safe to be eaten, although I wouldn't recommend it, at least until we figure out how to make a proper strawberry flavor. Our tests were done on multiple paper and cardboard types, and on some polymers as well. We're starting testing on a wide range of biodegradable polymers. After 1,000 bending cycles, the resistance would double. So they're still under development, but initially the research seems quite promising. Anyways, properly working RFID antennas were created. After removing the chip, you can even easily toss such a sample into the fireplace, although I would prefer you use different degradation methods. We have confirmation that proper biodegradation occurs both with substrates and matrices, so the only residue may be a small drop of silver. Last technique that is applicable mainly for the high power electronics is low temperature joining technique. Let's dive into that topic for a moment. I'll say about a few words about the technique itself. And what is quite surprising, it is also applicable for flexible uses. And what you should know, as a effect, the joints are pure silver. So it is something that can be quite nicely managed to be recycled. So low temperature joining technique allows for sintering of metal powders at temperatures well below their melting point. To a certain extent, it is possible to lower the sintering temperature of the metal in the assembly by adding high pressure. Mounting in this technology consists of 5 steps: printing of the paste, drying, removing organic compound by annealing, arranging the mounted element, and sintering the layer with the pressure of the mounted element. The most commonly used materials for sintering is silver. Of the other materials considered, gold and platinum are too expensive, and in case of copper, assembly in a nitrogen atmosphere would be necessary. Silver sintering may be done in a normal atmosphere. The melting point of silver is 961 degrees. Sintering silver in the presence of glass frit reduces the temperature to 600 degrees, but it's still too much, way too much for many electronic systems. And at the same time, the glass frit deteriorates the thermal conductivity and electrical resistivity of the layer. Using the low temperature joining technique, with silver microparticles, it is possible to obtain a single third layer at the temperature of 400 degrees. And with silver microplatelets, you can reduce this temperature even to 300 degrees, although the pressure used is the limitation. It ranges from 20 to even 80 megapascals, which may damage the attached electronics component. In not only mine research, silver nanoparticles were used to reduce that. In our case, we developed nanoparticles during one of our projects. The particles are characterized by an average grain diameter of 6.5 nanometers, and they have quite high content of organic shell to prevent grain agglomeration. The first joints we made using only silver nanoparticles as a functional phase were sintered in 300 degrees and 10 megapascals. Later, we reduced the pressure to 5 megapascals. The joints were characterized by shear stress resistance of about 10 megapascals. so comparable more to adhesives than to soldiers. But SEM and EDS photos showed that there was quite high amount of organics within the layer, impacting the conductivity, because the conductivity was quite similar to soldering, and mechanical parameters. And that is why we used a mixture of two sizes of silver particles: nanoparticles mentioned earlier and silver microplatelets. Conducted tests confirmed that McGeary's work that you can see in the slide really works. So the lowest porosity was achieved with 25% of the silver nanoparticles and 75% of the microplatelets. It is also worth mentioning that this approach nicely works in bigger scale or in different materials. So for example, in adhesive preparation. To reduce the porosity even more, we used a method of decorating silver microparticles with silver nanoparticles. During sintering, the nanoparticles acted as a glass fluid, wetting the grain surface at the contact point, replacing the solid layers at the intergrain boundaries in the neck area. At the same time, the molten nanoparticles fill the pores that are formed, reducing the porosity of the layer. Replacing the electrically non-conductive glass fluid with conductive materials allowed for a lower electrical resistivity and higher thermal conductivity of the layers, while maintaining a low sintering temperature within 300 degrees, which is important in assembly. In turn, we reduced the amount of expensive nanoparticles. With that, we lowered the content of organic substances acting as a coating and lowered the overall cost of the material. And we achieved shear stress resistance of 20 plus megapascals, so comparable to soldered, and electrical resistivity 5 times better than soldering, with only 2 times lower resistivity than for bulk silver. And subjoints were tested not only electrically, but thermally. So thermal analysis was conducted with laser flash analysis and comparative method, and then we confirmed it with theoretical simulations based on the Wiedemann-Franz law. Thermal conductivity was also about 5 times better than for lead solders, and it was about 200 watts per meter Kelvin. Such joints can survive easily 350 degrees. The layers would survive up to 600 degrees, even though they were sintered in lower temperatures than we used later on during our tests. We used even 30 ampere current for the test. And going to the end, that was the biggest surprise, and that is why I'm speaking of this technique right now. So the silver sintering method would allow us for making flexible joints that would easily survive 10,000 bending cycles. We had some samples, but not in such amount that it's statistically important that would survive 20 or even 30,000 cycles. We were just curious. And the resistance change was within 10% of the initial resistance in our best composition. But it is necessary to remind that with such high temperatures, for flexible electronics, we can use just some materials, for example, DuPont's Kapton foil. But with high thermal conductivity, even high power diodes worked quite nicely assembled on flexible foil substrates. So by comparing the developed technology with others, we were able to obtain lower resistivity, higher thermal conductivity, and comparable resistance to shear stresses. At the same time, the process temperature wouldn't exceed 300 degrees. We can even go a bit lower, although it may affect the parameters, with 5 megapascals pressure, which the electronic components survive easily. but there is a disadvantage. So this method requires at least 30 minutes joining time with applied pressure. It's quite a long time, but we built a press allowing for to create multiple sinter joints at once. With that, we lose concerning the sustainability because of the temperature of the process. But later on, with high thermal conductivity, high electrical conductivity, we're gaining due to the to small losses of the energy. So, to summarize my talk, we have more options than just adhesives for flexible joints. And silver sinter joints are better for heat removal from integrated circuits and high electrical conductivity. Although for stretchable joints, still the main option are adhesives. Washability may be improved with encapsulation or lamination for non-stretchable substrate, but for e-textiles, it's still encapsulation as the best option. And concerning the sustainable materials, they're improving, but still are mainly in research. Thank you.
Thank you very much, Professor Jerzy, for this interesting talk. I think it's really relevant nowadays, that this is for stretchable electronics. In the audience, if we have questions. I have two questions for you. So basically, you mentioned, so it's quite relevant, the application that you showed, and for the wearables and so on. But if you want to miniaturize, so if you want things with resolutions, so lines with less than 100 microns, do you think that you have more issues in that aspect? And if you want to correlate with ICs, basically, so if you want print electronics with integrated circuits, that can be a issue, right? Because for that we need lines really thin, and that changes everything, right?
So we used my adhesives for the smallest lines were for NFC chips with 100 micron width of one contact pad, and we are able to attach them quite nicely in 60 degrees centigrade. The issue that may happen in this particular case is that with this VJ adhesive that I use, I use quite big micro platelets. So the screen printing is an issue because it clogs the mesh. When I tried to improve the adhesive for this particular sizes, I had to reduce the area of silver particles, which momentarily reduced or actually rose the resistivity of the material. The resistance of the joint rose twice, actually.
And
to go below that, it depends on the substrate, but I think it would be applicable. Well, with screen printing, you can try to go as low as 50, even 30 microns, but you really need a very good printer and a very good specialist doing that.
And the VJ pastes that you show, they are commercial or they're just your own?
The VJs are my own. We have, at our team, our main advantage is creating materials by design for different uses, whether these are sensors or adhesives or just conductive paths.
Yeah, thank you. So, and then just to finalize, so in the end, you mentioned that it would be nice to use other sustainable materials as a conductive layer. So as we see, mostly in literature, they are typically based on silver, but right now we have other materials based on 2D materials, so MaxScenes. Do you think already in pastes using MaxScene Maxine materials?
I haven't used that yet,
Okay.
but I will definitely have to.
Okay. So, any more questions? So, not thank you very much again, Professor Jerzy,
Thank you.
for this interesting talk. And so our next speaker